So here in 8.2, we're going to continue our study of don't cares in multi-level logic networks, how they arise implicitly as a consequence of the structure of the network. In the previous lecture, we showed how some don't cares arise because of the structure of the logic in front of a node in the Boolean network. What we're now going to show is that it's also possible for the nodes in back of your node, the nodes between you and the output, how the structure of that logic can also create internal don't cares. So let's go back to our example and see how that happens.
So let's continue our tour of how you pull implicit don't cares out of a multi-level logic network. What I had sort of shown you in the previous lecture was that I could pull a bunch of don't cares out of the inputs to the x, b, and y inputs to the F node. And roughly speaking, I'm just going to draw sort of a line through this logic network, which is what we were showing previously. So this is a Boolean network that still has x equals ab as a node, y equals b plus c as a node feeding, and f equals xb plus by plus xy node. There's a new node here, a node between f and the output called z equals fxd. And what I sort of showed you in the previous lecture, which was 8.1, was looking at nodes in front of the F node, I can find some patterns of x and b and y. What I'm going to show you now in lecture 8.2 is I'm going to show you that if you look at the nodes behind node F, the nodes between F and the output, there are some more don't cares. So here's the new question I want to ask. 1, suppose that F is not a primary output, so F passes through some other stuff, the Z node, to become a primary output. When does the value of the output of node F actually affect the primary output Z? Or said conversely, when does it not matter what F is because the value of F does not affect Z? Let's go look at patterns of the F, X, and D inputs at node Z and see if we can find some of these values that make Z not care about F. So what we're going to look at now is inputs to the Z node. We're going to see if we can find some interesting context, some interesting relationships. So let's ask the question, when is Z sensitive to the value of F? So I've got the logic network shown again here. X equals AB, Y equals B plus C, feeding into the F equals XB plus BY plus XY node, whose output goes to the Z equals FXD node to become the primary output Z. And I want to ask the question, when is Z sensitive to the value of F? And so I've got a table. It's also got 3 columns, like the last lecture. The columns are F, X, and D. And the column to the right says, does F affect Z? Now, note please that the rows of the table are not in Boolean, the standard sort of Boolean order. What's actually happening is the first 2 rows are when X and D are zeros. And then the leftmost column is when F is 0 and 1. And then the second pair of rows is when X and D are 0, 1, and again F moving from 0 to 1. The third pair of rows, X and D are 1, 0, again F moving from 0 to 1. The fourth pair of rows, X and D 1, 1, F moving from 0 to 1. The reason I have F highlighted in a different color is I want to ask the question, whenever X and D take on this set of values for the first set of rows 0, 0, does F affect Z? If F changes from a 0 to a 1, does anything happen? So let's just go look. What happens if X and D are 0, 0? Does it matter if F is a 0 or F is a 1? So there's a little arrow here that says delta F between 0 and 1, and the answer is no. Look, the Z node is basically an AND gate. If X and D are zeros, no, Z is a 0, and F does not affect Z. What if X and D are 0 and 1? Again, if F is a 0 versus F is a 1, does it actually affect the Z node? No, it does not. It's an AND gate. Z is still a 0. What if X and D are 1 and 0? Does it matter if F is a 0 or a 1? Does it affect the Z node? No. Hey, it's an AND gate. Z is still 0. What if X and D are 1 and 1? Now, does it matter if F is a 0 versus F is a 1? Yes. Now it matters. Now the output actually depends on F. But in the other cases, when X and D are 0, 0, 0, 1, and 1, 0 respectively, Z does not depend on F. It doesn't matter. So, question, can we use this information to find new patterns of x and b and y to help us simplify the F node? Because remember, these are not patterns of x and b and y. Like the things we did in the previous lecture, we start by looking at the nodes that are contextually next to the node we want to simplify, and we ask some questions, and then we use some techniques that you don't know yet that are in the next couple of lectures to sort of pull out the patterns that are of value, the impossible patterns. So looking at what we now know about f and x and d, can we find some patterns to simplify x and b and y? And the answer is yes. So just to be clear, what patterns at the input of f, okay, are don't cares because they make the z output insensitive to changes in f. And again, it has to be values of x and b and y. And what we discover when we stare at the table of f and x and d, the does f affect z table, what we see is that if x and d are 0, 0, if x and d are 0, 1, if x and d are 1 and 0, then z is insensitive. But I only get to look at patterns of x and b and y. I can't pay attention to the d. So the only thing that's of consequence here is that I notice that whenever x is 0, and I'm just going to go highlight that over here, whenever x is a 0, it is the case that the network output Z is insensitive to F. And so the pattern that I can get, that I can pull out that's legitimate for me to use, is that a pattern of X, B, and Y where X is a 0 and B and Y are I don't care, that is in fact a new don't care. That's a don't care because the output is no longer affected by my F value. So, can we use this new don't care pattern, x equals 0, to simplify f? Yes, we can. The pattern xby equals 0, don't care at the input of f will make the network's z output insensitive to changes in f. And so I've got the same network shown below. X is AB, Y is B plus C. They both feed the f equals xb plus by plus xy node, whose output passes through z equals fxd. And I've got the Carnot map drawn up again. XB on the horizontal axis, 4 columns, Y on the vertical axis, 2 rows. And I've got the entire right 3 columns of the Carnot map are either don't cares or ones. The top row is don't cares, the bottom row 1, 1, don't care for the right 3 columns. And if I now put the x equals 0 pattern in as a new kind of a don't care, what I get is that everything where x is a 0 becomes a don't care. So the entire first column, 0, 0, becomes a don't care. And the entire second column, 0, 1, also becomes a don't care, the 1 in the 0, 1, 1 slot being replaced. And so the amazing thing now is that the entire Carnot map is either made out of don't cares or it has a single 1 in the XBY 1, 1, 1 cell. And so the unavoidable conclusion is that the value of f, if I were to actually sort of simplify this thing, is that f is just equal to 1. And if I, just do it, oh, there it is. F is 1. That's what I'd circle in the Carnot map. I'd circle every one of the 8 squares in the Carnot map. So that's pretty amazing. As a consequence of having the x node and the y node feeding the f node, and having the z node consuming the f node before it actually generates a real primary output, f, which started out as something kind of complicated, is replaceable by the constant 1, just because of all of these implicit don't cares that happen because of the structure of the logic network. And so if we, just go look at this, look what happened to f. On the top I have the old network. X equals AB is a node, Y equals B plus C is a node. They feed the F equals XB plus BY plus XY node. That in turn goes through the Z equals FXD node, become primary output Z. What happened? Well, down below I've still got the X equals AB node and I've still got the Y equals B plus C node and a B primary input, but they feed a node that just says gone. I don't need the F node anymore. I can really replace that with a 1 in the Z node. it turns out that I still need the X node to create X for Z, but I can also put a big X through the Y node. I don't need the Y node either. This network has become dramatically simplified because I was able to extract some don't cares from the structure of the rest of the Boolean logic network, pass those don't cares to the two-level optimizer, something like Espresso, that's operating on the two-level form inside every node, and simplify things. So this is a really big idea. So here's a summary of where we are in this implicit don't cares story. Don't cares are implicit in the Boolean network model. They arise from the graph structure of the multi-level Boolean network itself. Implicit don't cares are powerful. I'm going to put an exclamation point by that. They can greatly help simplify the two-level SOP structure of any node. But implicit don't cares require computational work to go find. For this example, we just stared at the logic to find the don't care patterns. It is clear that we cannot do that. There's got to be an algorithm, and that's what we're going to do next. We need algorithms to do this automatically. So let's go look at how we can use all the nice computational Boolean algebra that we learned at the beginning part of the course to actually pull these don't cares out.